Good morning, everyone. I am indeed today going to be talking about new 18.0 operators. I'm also going to be talking about an idea or a style or a mindset called tacit programming, why you might want to use it, why you might not. And I'm going to be introducing these new operators in Dyalog 18. And if JD gets an alternate title, so do I. First off, tacit programming. What do we mean when we say tacit programming? Well, tacit just means not saying something. So tacit programming is not just code that doesn't say anything, but it's code that doesn't mention specifically the arguments to functions. So in traditional APL, of course, you'd write, they called them defined functions, we call them tradfns. Now we've got these other functions called defns as well. But the way you'd write them is that with a tradfn, you'd name what are the names of my arguments, and then you write out some code that uses the arguments. In a defn, you'd write out some code that uses arguments, they've always got the same names. With tacit code, you never even mention the arguments. You leave that up to the programming language and up to the definition of the programming language to determine how your arguments move around. So here's a pretty simple example of tacit code. To write a program that sums a vector, you could write a defn that says sum this vector, or you could tacitly just take the sum function and give it a name. So clearly in this case, the tacit function is much simpler. It's less code. This is a very simple example, and in early APL, which had the reduction operators and inner products, this is pretty much all you could do. As APL has advanced, we've started getting some operators that, rather than doing things with arrays maybe, they work more with functions. And their role is just to move arguments around and get arguments into the place where you want them. So this enables not just slightly tacit programming, but fully tacit programming. Here's another example of a small tacit function that you can write with one of these operators. You've got here a defn that refers to its argument twice, and you can actually write it as a tacit program that refers to its arguments none by using the commute operator, which repeats the same argument twice. Now, the thing to notice about these examples is that the defns, because they mention their argument, make it clear that these are functions of one argument. You can pass another argument on the left, but it'll just ignore it. In contrast, the two tacit functions here both actually have another meaning when you give them a second argument. So sum becomes a windowed reduce, and square becomes multiplication. And in both of these cases, these are not really particularly useful alternative functions. They're not that closely related to the original definition. But one thing we'll see is that tacit programming does sometimes enable you to make functions that are closely related to the original function, and it gives you more flexibility in your code because you can write a single function that does two related things that are both useful in your program. So to demonstrate tacit programming, I'm going to work with playing cards a little, just to have something to look at. So here I have an explicit function, disp, which displays a playing card. So I've decided that a playing card is two numbers. It's got a suit, which is one of the 13 suits, 2 to ace, and it's got a rank. It has a rank, and it has a suit, which is one of the 4 playing card suits. So to display it, we take these two numbers, and we use them to select from lists of the possible card ranks and the possible card suits. And we can get all the cards with iota 13.4 and display them all with disp each. APL won't color them for you. Had to do that myself. It's very easy to turn this program into a tacit program using a bound argument. And in this case, what we see is that because binding a function to an argument makes a function that's only monadic, we haven't actually lost any context. These they don't mean exactly the same thing. The first one will ignore a left argument, the second one will give you a domain error. But they both make it clear that it's a function of one argument. So in this case, you haven't actually lost any context. I'm going to make a few improvements to this function. The first is you don't necessarily have to understand how this works, but rather than using pick for indexing, later I'll need a more general index utility function that just picks the major cells of its right argument. So the major cells are arranged one-dimensionally, sort of. So one index lets you pick a major cell. And this function I takes each scalar from the left argument and uses it to pick a major cell. So I'm replacing pick with I here. In this case, they do the same thing. Later, they won't. And also, I can add even more context to my tacit function by specifying that it works with rank 1. So I use the rank operator here to say the argument to this function should always be a vector, and if it's not a vector, it will just work independently on the vectors of the argument. So after we can display playing cards, the first thing we might want to do with them is pick a card, any card. This might be from a deck of cards or a hand of cards. What I'm going to say here is that the argument is some matrix where the rows have length 2, so each row is a playing card, and I'd like to pick one at random from that. So the way I can do this is by taking the number of cards that I'm choosing from, taking a number up to that number, and using it to index into those cards. So here you can see I have a deck consisting of all the playing cards. It's a 52 by 2 matrix, and I can pick a random card from that. I can make this into a tacit function using a train. Now, here, I'm not going to necessarily have enough time to teach you how to use trains completely, but I hope I'll at least be able to explain what, maybe how trains work, what the main idea is. But I can rewrite this as a train with a few modifications. First, I bind the roll function to the tally function using a jot. And second, I replace this argument on the right with just an identity function. So I replace the argument with a function that returns the argument. And the interesting thing about this function is that, of course, it has the same functionality as our explicit function. It doesn't return the same card, but
not necessarily.
Who knows how APL works? It has this additional functionality where I can pass in a left argument and say, I want to deal out 5 cards that are all different from each other. So the reason that I'm able to do this is, well, there are a number of reasons. Every part of this expression actually has to be designed so that I can usefully use it in an ambivalent context, either monadic or dyadic. So first, of course, the roll function has a related dyadic function called deal, which gives me this functionality. Second, the particular composition I'm using here allows me to apply this right operand only to the right argument and the left operand ambivalently. Third, I've used the right identity function. There's 2 identity functions, and they're both the same monadically and different dyadically. Usually we use the right one because it's more useful in a dyadic context to have the right argument. So all these things together allow me to have this function that's useful either with or without a left argument. And the last thing that enables this is the way function trains work. So a little about trains here. A train is what you get, a 3 train is what you get when you write just 3 functions next to each other with no arrays involved. So this forms a function, and when you apply this to arguments, it applies each of the left and right functions to those arguments, and then the middle function between them. And so I've written here the paths that arguments take when they're passed to functions. Now that probably seems pretty obtuse, maybe even occult. That's not the way I think of it. The way I prefer to think about trains is that these 2 arguments, alpha and omega, are just a kind of context. And within this context, f and h are not functions, but they're just values that depend on the context. So I think of a 3 train as just a single function g applied to 2 other functions, and it returns a function, which maybe that's not even a function, maybe that's another value that depends on context, and I can pass in the context by passing in 2 more arguments, alpha and omega. This view allows me to extend my thinking even to larger trains. So with larger trains, in this mindset, it's really just another APL sentence. It's a bunch of values that are being combined together with functions. And the only trick here is to know that the parsing is different, because there's no way to distinguish an argument from a function anymore. We have to assume that every function application is dyadic. So like when reading APL, we move right to left. But rather than every time we find a function, checking whether it has an argument on its left, we always assume that the thing on the left is an argument. Except for the very last function, where if there's no function on its left, if we have an even number of total functions, the last function is just applied monadically to the result of the rest of the train. And this gives you, in particular, a two-train, where you just have a single function applied to one other function, and that function is called on the arguments, and then the other function is called on it. So here's a more concrete example of how I can use trains and how I can think of them as just working with context. I have here a fairly long function, validate, which takes a hand. Maybe I'm playing 5-card stud and somebody's dealt me a poker hand. And I'd like to make sure that it's a valid hand. So the things that I want to check are that the shape is correct. It has 5 cards, and each has a rank and a suit. All the ranks, that's the first column, are one of the 13 possible ranks. Every suit is one of the 4 possible suits. All the cards are unique. I'm expecting that the dealer is dealing from a single deck. If I have 2 cards that are the same, the dealer is doing something screwy. So then once I've done all these tests, I combine them together with just Boolean AND to make sure that all of these things are true. Now, every individual validation function here can actually be written as a train. So on the left, I have this completely explicit model where in every line, I'm referring to the argument, and I'm passing the argument right directly into the function where I want to use it. When I make each line into a train, instead, I'm sort of writing a function for the entire test and then passing the argument into it. So each of these tests is now its own function. And on every single test, I'm just calling it on omega. Now what we can do with a train is to take this omega and pull it out of the individual lines and into the last line. So now I'm treating omega as context that you should know about when you're reading the rest of the function. And then each of these functions, shape, ranks, suits, and unique, are understood as functions that take place in this context that I'm evaluating a poker hand to make sure that it's correct. And I can even go further with this. I can make it more tacit, because the argument's only used once in this function now. I can actually remove the whole defin structure and make this into a single function validate, which is composed of a bunch of other functions ANDed together. Now at this point, I've lost some of my context. I've lost the fact that this is meant to be applied with a single argument. So if I were writing this in source code, I would then have to at least write a comment to say, hey, there's just one argument here, and maybe what the argument is for. So as you become more tacit, yes, you're writing less code, but also you're relying more on understanding of how it's going to be called. And of course, if you feel drawn to remove all the context, you can do that with the famous APL one-liner. And it's your job as a programmer to find somewhere between here, and preferably not either endpoint. Okay, one of the things that I used in that function was to have a train, but it's not a train of 3 functions. The left argument is actually an array. And so once you understand it, in this model as just functions with context, it's pretty simple to see that this function a, or this value a, you can think of it sort of as a function that just ignores its context. It's so h is a value that depends on context, and a, this array a, is not. But one of the very tricky things about trains for beginners is that even if you understand this model, what happens is you may try to actually write an array on the right. Why not? Both of these functions are treated the same. And because of just the way APL is parsed, in order for something to be a train, there has to be a function on the right. That's the only way the interpreter can know that it's starting a train. So that actually doesn't work. So making it easy to do that, to just flip the arguments to this train, is one of the things that one of our new operators enables us to do. And so finally, in APL, we have now introduced the simplest operator. It took us a while, but we got to the simplest one. This operator is called the constant operator, and it just takes an array and gives you a function that always returns that array. So you can even think of a train with an array left operand as implicitly calling the constant operator on that array. One thing the constant operator enables us to do with these ranks and suit functions is to swap the arguments to membership, to write it in what may be a more natural way for an APLer. Now that we've got these functions flipped, we can see that actually they share a lot of structure. So one thing we might do is combine them. We can write this tacitly. So at the end of our tacit function, we're going to just and reduce both of the Boolean vectors that we have. And then this part to the right is a train. Here, rather than taking the left column with tac reduce and the right column with tac reduce, we're going to transpose the whole hand and split it so that we get two vectors, one of ranks, one of suits. And then we say member each with, again, a constant right argument. And we can simplify this further. We can say, well, rather than having this constant, rather than writing iota each and membership each and reduce each, we'll just have a single function with each in the middle. And then we use a jot here to apply iota only to the right argument. And this and reduce membership is a single function. The reason that I've combined that into a two-train is because I think of that as a single function. So a two-train allows me to put these two things that really belong together. I'm saying everything in the left argument is in the right argument. It's a subset function. And I've also used a two-train for this split transpose, which I think of as a single function. And the reason why a two-train might be better than a jot there is that transpose works meaningfully with a left argument. So this function now, it can work not just on two-dimensional hands, but if I want to have a three-dimensional hand, and I just want to transpose the last axis to the first one, I can do that using the function split transpose with a left argument. But gosh, I've introduced a lot of parentheses there. It would be nice if there were a way to write split transpose without these parentheses, say. Constant gives you some other useful things. You can use this constant function to generate constant arrays where every element is the same. This is something that often you'll have to play with shapes a lot to do. And constant combined with APL's very powerful operators gives you a whole lot of tools to not have to do that. So for example, you can call a constant function each on an array to get a constant array of the same shape. One really cool one is that you can call a constant reduce on an array to get an array with the same shape except one of the axes is dropped. So if you use slash bar, you drop the first axis. If you use actually slash bar with a rank, you can drop an arbitrary axis. You can even use an outer product to combine the shapes of two arrays. So this thing here says the shape of alpha and the shape of omega put together. And I've used another funny symbol here. I said earlier that I'd like a different way to write two trains without the parentheses. That's another addition to version 18. So it looks like we're not really doing much actually here because Atop is already there. You can already write it as a two-train. But having this operator notation makes it much easier to put an Atop in the middle of a train, say. It makes it much nicer to look at source code. And it also means that you're not really pushed into using jot just because of the syntax in situations where you would prefer to use Atop instead. So Atop is like a 2-train. If we straighten out this diagram, we get another diagram of how you might view Atop. It's one function applied to another function after it's been applied to 2 arguments, or only 1 argument if there's only 1. So for example, disclose Atop rotate, you might, if it has no left argument, it'll reverse the array and then pick the first element, which is the last element of the first row. If there is a left argument, it'll rotate the array and pick the first element. So that actually gives you indexing with quad IO 0. Kind of interesting. One thing that if you do tacit programming, you'll use Atop for all the time, is to write f atop the left argument, or f atop the right argument. And this is directly analogous to in a defin just writing f alpha, or f omega. But if you're in a train, it doesn't require parentheses because the Atop binds more closely than trains do. Lastly, if you're doing tacit programming and you want your middle function to be replicate or compress, this is going to be a problem for you because you're writing function slash another function. And so the slash treats its function on the left as an operand, and it turns into an operator, reduce. This is a pretty big problem in tacit programming. And Atop gives you a nice way out, which is to write right tac atop compress. So of course right tac atop does nothing. You're composing something with the identity function. But in this case, it allows you to fix the syntax and say, no, I want this slash to be a function. Finally, the last operator we're introducing in version 18 is also by far the most useful. This is giving us new functionality in terms of tacit programming, much like the tilde diaresis that copies the right argument over to the left argument does. So before, in order to take one function and apply it to both arguments of another function, you would have to either name that function and then write the name twice, or you'd have to combine the arguments in an array and use each. That's really messy. So instead, we have this new operator over, which enables you to do that. And I think you'll end up using this all the time. An example here is if I have a function that turns poker hands into their ranks, so something that in APL sorts the same way that poker hands sort. And people say tacit programming is complicated, but this hand rank function doesn't have any trains or tops or overs in it, so I don't know what they're on about. Anyway, if you spent some time and written up this function, and you have another function to compare two values, so CMP is going to give me a -1 if the value on the left is larger, and a 0 if they're the same, and a 1 if the value on the right is larger. And you want to compare two poker hands. All you have to do now is compare over hand rank. So this applies this rank function to both arguments, and it turns each one of them into a rank, and then compares them using APL's total array ordering. So, for example, here I've written one hand, I have a full house, and I want to know whether that's better or worse than a straight. And I do this, what I do is I just undisplay each argument, and then I compare them to see which one's better, and it tells me a full house is better. Unfortunately, inverse doesn't do this yet, because it doesn't understand, it doesn't work with my disp function, because it doesn't understand rank, but I will try to get it working for version 18. I've got some ideas. So, over, I've used it a bunch of times here. It's a pretty nice way to move functions around. Here's just a diagram of now all the composition operators. What I mean by composition operator is an operator that doesn't really do anything. It doesn't look at what the elements of an array are or anything at all. All it does is take its operands, which might be functions arrays, and apply those functions to other arguments. And I've written here the structure of each of these operators. So the top row are operators that are from version 17.0 and 17.1, and the bottom row are operators that are new in version 18.0. One other change we've made is that the jot, we officially called the compose operator. We are changing the name in version 18 because all of these operators are compositions. It doesn't make sense to call one of them compose. So the name for two functions jotted together is going to be beside. You put f beside g, and that describes how it's evaluated. It's the same as if you had just put f beside g in an APL sentence. And when you combine a function with an array to say this, it should always use this argument, that's called bind. So this is just a diagram of all our new composition operators. I think they form a pretty nice set, and I'm happy to have them in version 18. If anybody has questions, come up to the microphone. Yeah.
It's just a question about the symbols. Atop, is that a different symbol than the rank?
Atop is the same symbol as rank.
The same symbol.
Which, yeah, it's not perfect. Typically when you use rank, the right operand is always just a few numbers. So it's pretty easy to see if you actually use these in code. Well, here's a circle diaresis.
Right.
And I'll look at the right argument. Oh, it's a 3. This is rank. Or, oh, it's something other than a 3. This is in Atop.
Okay. And the over one is the new.
Yeah.
That's not going to cause any confusion, I'm sure.
Less than you think. Go ahead.
Right. Just a question regarding the naming, because you're introducing new names now. I would propose to think about beside and
oh boy, have we thought about beside.
Maybe name it after. That's how the math guys do it, and it would be F after G, and it's also very clear.
My complaint about taking the name from a mathematical composition for beside is that, sure, this version is mathematical composition, but that's also true for both Atop and over. And this version doesn't really look like something that you use in mathematics at all. I guess it's composition in a language with partial application,
right.
But it's not, I don't think it's a good analog for mathematical composition. I think Atop is a much better analog because you'd say, here I'm composing a function of one argument with a function of two arguments.
Okay, so I'm
So I don't
completely
like
fine
that
with
application.
dropping the name compose, but I was proposing to maybe think about the word after instead
Yeah.
of beside.
That is one name we've considered. And we're not set on beside,
All right.
so if you have other ideas, do tell us. But we have considered after. That's the reason that I don't think it's as good of a choice.
So last year, Jay presented also obverse and under. What happened to those?
Exciting things happen to under. We have a great proposal. I have a great proposal called structural under, which I am already excited to present next year. If you want to talk about it with me, I am very happy to tell you about it. I won't do that during this presentation, but okay. Under is coming. It's going to be better than ever. It's going to require a lot of work to implement, which means we're not going to get it in version 18. Version 19, I'm pretty sure.
Thank you.